In the last section, we'll look at the LCP array, which will turn out to be the solution to both applying the suffix array in the same examples we've seen for suffix trees, and to finally clear this black box of how to compute the suffix tree, the full one, in linear time. So far, we've only done that for the suffix array. And to motivate that, let me remind you or ask you to remember what we needed for the first of these more interesting applications, which was finding the longest repeated substring in a string. So again, this was find some substring in the text that occurs in at least 2 positions. It's fine if these are overlapping occurrences. We could solve that in linear time using suffix trees. And we used some features of the tree there. And that will guide us towards what's still missing if we just have the suffix array. There's really just one answer that's definitely needed. Let's get at least up to 50 again. Unless we never get there. Yeah, I think it fizzled out a bit. So there's been votes for most answers, but the majority is on the right track. So if you just remember from from yesterday, basically, the key feature that we needed was the string depth of internal nodes. We needed the internal nodes to iterate through in particular. So just as a reminder, the algorithm was very simple. If you have the suffix tree available, you compute the string depths of the nodes, or you remember that it's actually a compact trie and you have the string depths anyways. And then you find one of the internal nodes of maximal depth, maximal string depth, and read off the path from the root to that node. So in our example, we found that there's 2 solutions here. The deepest are tied for these 2. It's either Ben or Anna. Both is the longest repeated substring. It doesn't necessarily have to be unique. So if we just have a suffix array, it might be not so clear how to do that. But we can indeed add a second array, and then it becomes possible. That will be the LCP array, the longest common prefix array. It's a term that we've had already on the slides back then. It stood for taking any 2 suffixes, give me the longest common prefix, the longest common part that they share. But it turns out that's too much. If I can take every pair of leaves, that would be quadratic in size, so we don't even have the time to write that down. But we can strip it off to only look at adjacent leaves in the sorted order. So the key definition here is this one. The rth entry in this LCP array is taking the leaf, the rth leaf, leaf of rank r, and leaf of rank r minus 1, and compute their longest common prefix. So in a way, what we have is we have those leaves here in that order. That's the leaf array, the suffix array. Right? It has 9, 5, 7, 3, and so on in that order, if you check with the example from before. And the LCP array has for adjacent pairs in here a number, namely the string depth of their longest common, so the string depth of their lowest common ancestor in the tree. So here it would be 0. Here it would be the lowest common ancestor is this node, so it would be 1. For these two, it would be 2, because that leads to that node where these branch off. The lowest common ancestor of those two is this, which is 3, and so on and so forth. Here we go back to 0, then we have another 3 here. Nobody can read that. Another 3. Maybe I should, this could be mistaken for zeros, I guess. I'm just trying to show what leaves they correspond to. Here we have another 0 because the lowest common ancestor is the root. Here we have 1, and here we have another 2. So if I straighten this out, the leaf array would be 9, 5, 7, 3, 1, 6, 0, 8, 4, 2. That's L. And, you know, the indices would be like this. And the LCP array, you should really imagine it sitting between those numbers. So it should sit here 0, 1, 2, 3, 0, 3, 0, 1, 2. Unfortunately, we can't really tell most programming languages that we want this to have index 1.5 and this index 0.5 and 1.5 and so on. So instead it's shifted. So this is index 1, 2, 3, and so on. So it starts with 1 here. Unlike most of our arrays, we don't use the 0 entry for this one. So that is LCP. Okay, that's from this example. That's what you should imagine here. Now for the longest common substring problem, all we need to do is find the largest entry in the LCP array. And we find indeed there's 2 times the 3. So that's the length of the longest common, of the longest repeated substring. If we want to know what string that is, we have to check at what indices that occurs. And that gives us the two suffixes that start with that thing. So here's that connection drawn a bit nicer again. That's the leaf array. That's the suffixes that it corresponds to. Here are the longest shared prefixes, the longest common prefix between any adjacent 2 suffixes. Nothing for these 2 because they differ on the first character already. And for some others, there's a longer common prefix, up to 3 characters here. That's why the LCP array looks like this. Now, you can draw the same information slightly differently as intervals, because it turns out the things that are shared, so it's not just these numbers go up and down. Also, if you look at the part that is shared, A, AN, ANA, they all share an A at the beginning. So you can say there's an interval among the sorted list of suffixes where they all start with an A. And nested within that interval is one where they all start with AN. And so on and so forth. Sometimes these are just a single pair of suffixes. Sometimes there are more. And here comes the cool trick. So that's the part to pay attention to. These LCP intervals correspond 1-to-1 to the nodes of a suffix tree. So again, if I have the suffix tree, every internal node corresponds to such an LCP interval. So a range in the sorted list of suffixes and a prefix that everything in that range shares. The root corresponds to this dummy shared prefix of the empty string that everyone starts with nothing. Okay, fine. That's kind of a corner case, so that everything is covered by one interval. Then the children of the roots, there's one that goes to A. That's this range. That's the LCP interval where everything starts with an A. And this holds true in the other direction. There's nothing that only starts with B. The whole thing is contained, so everything that starts with a B actually starts with BAN. That's why there's an internal node for the prefix BAN, but nothing in between. There's no other internal nodes before that. So it's really a one-to-one correspondence. And that might help you appreciate that from just the LCP array and the suffix array, you can reconstruct everything that's in the tree. All the information is in there. It might be a little bit hidden, or it might be a little opaque to see it. But the key information is there. And so you can indeed reconstruct the tree with a simple algorithm from those two arrays. We don't do the full code, but you'll do an example in the tutorials to practice it a bit. In a way, you can do it like this. You align the suffixes in sorted order. And if you have the longest common prefixes, it's easy to also determine these intervals. It's just ranges where there's the same minimal number. So this A corresponds to a range where the LCP does not drop below 1. But there is one occurrence of that number. And from that, you can reconstruct the suffix tree. What I want to show you here as the last bit is, where does this LCP array come from? I've introduced yet another array, so we need an algorithm to compute it. And again, it should be in linear time to be interesting. So the last section will be about constructing the LCP array efficiently. You can go by the definition and compute it naively. Often that's not very slow, but in the worst case, it takes linear time for each entry, so quadratic overall. Again, a possible worst case is the degenerate text of all A's, where you have these long shared suffixes all the time. The insight to speed that up is if you imagine doing this naive algorithm for every next pair of leaves, you start comparing from the beginning how many characters are there the same. Suppose you do that and you have one really long entry. For example, here you have this valid, grammatically correct English sentence of buffalo, 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 buffalo. And you can add more buffaloes to this. If you haven't seen this, a fun one, but it's a bit beside my point. If that's your text, then you may have these two suffixes in sorted order that share a long shared prefix. Whenever you have this, we actually are guaranteed to find more large values, and we can kind of deduce those. Let me show that on an example, and then we'll do the proper algorithm. So suppose you have a first few of these of suffixes of this text in sorted order, and you found a really long common prefix between those two. Well, if I take off the first character of those two, then they become two other suffixes, but they still share a lot because it's just one character less. If they were the same for the first 18 characters, then chopping off that first character means they share 19 characters. They still share 18. The tricky bit is just to find where does that 18 go. We know there's two suffixes that have a longest common prefix of 18, but which ones? And what's more, it may not be that these are adjacent. and then they don't actually have an entry. There might not be an 18 anywhere in the LCP array because these two are not adjacent in sorted order. That's the slight caveat. But otherwise, this is the key idea. If you have one longest common prefix between two suffixes, then there must be many other shorter suffixes that all lead up to this long shared prefix. And so you can capitalize on that and amortize the cost. And that's what Kasai et al.'s algorithm does. The trick is to compute the LCP entries, the values in the LCP array, in a smart order. And it turns out the smart order is not going from beginning to the end of the LCP array, but to process the suffixes in the order of their length. So let me illustrate how this works on an example, and then we'll see the full code afterwards. So we start with the longest possible suffix, the entire text. Now we find where does this lie in the sorted order of suffixes. So we use our right to the right array, the rank array, to know the rank of this is 6. So I find it at position 6 in the sorted list. If I know that, I can go to position 5, the previous one. That's this one. And I can check how many characters do they share. Now this I do naively, so I go through the characters one after the other. They share these, they share this, but then it's done, right? Then the shared prefix stops. So I determined one entry, one longest common prefix entry, namely 3 at position 6. Okay, now we're trying to make use of that information. And the way we do that is if we now go to the next suffix in the text order, the one that just loses the B, I'll try to find again, where does this occur in the sorted list? I use my rank array. So I go to 4 and I find the one that's before that in sorted order. And here comes the trick. Because there were 3 shared letters earlier, if I just remove this one B at the beginning, I have 2 matches, 2 characters that definitely are the same without checking. So I don't need to compare those 2 again. These are for free. And I start comparing one character after that. In this case, there's one more character, but then the 2 strings differ. So I have another entry of 3. But I only paid 1 comparison to get it. The other 2 were for free. And that's all. That it keeps going like this. That's the algorithm. So if you go to the next position, we check where do I find that in the sorted order. Well, it's at position 9. So we jump down here. Now we look at these 2 strings, and we know they had a length 3 shared prefix before. If I lose the first character, there's definitely 2 that are shared. And in this case, that's also where it stops. The next character differs. So I have an entry 2 to go into my LCP array. And I paid a single comparison again. And we keep going the same way. In each case, we take the entry that we wrote into the LCP array last time, subtract 1, because we removed 1 character. And that's the number of characters we definitely have a match for. And the others we just naively check. For this one, we go over here. We know 1 character is inherited, 1 match. There's actually 1 more that we pay for. And then we get an entry of 2. We go to the next one, find where it is. We have 1 inherited match. That's the only one, so we leave it at that. So for the next example here, we don't have any inherited matches because 1 minus 1 is 0. And here indeed, the first character already differs, so we get a 0. And the same thing happens here again. And then for this one, we don't have any inherited matches, but we find by comparing that there's 1 character that matches. And that's all. If you write that down as an algorithm, it looks like this. We need the suffix array and the inverse suffix array to be computed already. We need that to go back and forth between those 2 left and right pictures. We need the rank array to go from a suffix here to its location in the sorted list. But then we also need the suffix array to go from position 7, position 6. Where does that guy start? I need to know where I have to compare. So I need both L and R. These are computed up front, and we know how to do that from the sections before from today. L remembers my, my match that I found so far. And then I go through all the suffixes in text order. I look where it is on the right-hand side. That's my to the right array. I take the suffix above me and find where that is in where that starts in the text. And then I do my naive check, but I start with these L matches that I inherited. So those I don't check. I start at I plus L and I minus 1 plus L, and keep increasing that as long as there's a match. Then I store my the prefix I found in the LCP array. And then for the next round, I remove one character, so L gets one smaller for the next round. It's fairly short code. It does exactly what I've shown you in the example. It's just a little, getting all the indices in your head is a bit confusing. I always prefer the example and then derive the code from that. Let's briefly analyze that algorithm because, yeah. They skipped the fire alarm last week, I think. I was hoping they might also delay it, but no, there we are. Okay, let's quickly analyze the algorithm because in a way it looks dangerous. It has this inner loop and it has an outer loop. So can we guarantee that it doesn't go quadratic? And the reason, again, similar to some string matching algorithms we've seen, is we can do an amortized analysis. We can separately count how often this comparison comes out as equal or as not equal. The not equals are easy because whenever I have a not equal, I skip this inner loop, so I can only have one mismatch for each outer loop iteration. So there's at most n such comparisons where the outcome is not equal. And for all the ones where I have the equal outcome, I increment L afterwards. But L is never bigger than n, and we always make it one smaller. So it's only make it one smaller at most. And so if I add this up, I have at most 2n comparisons that I spend where the outcome is equal. It's similar to KMP and some of these algorithms. It's kind of a potential or a bank account argument. We keep L from the round and we only adjust it slightly. So it can move up and down. But if it moves up a lot, then we profit from that for many future iterations where we can't have another expensive operation. If one iteration of the outer loop made L move very far and spend a lot of time in this inner loop, then the next iteration cannot do the same. Okay, so overall, again, it's linear time because all the key operations only happen a linear number of times. With this, we can puzzle together our algorithm for suffix trees. Again, the details you will try in the tutorial. You compute the suffix array and then the LCP array, and you use this connection with LCP intervals to know exactly which internal nodes there are, and so you can reconstruct the tree from that. These two things, suffix array plus LCP array, is also called the enhanced suffix array because the suffix array has been enhanced by the LCP array. But this really is a more general thing. It's a bit more tricky to reason about as compared to having the suffix tree explicitly. But it turns out you can simulate everything that you can do in the suffix tree. You can simulate based on these two arrays with maybe extra tricks, but it's essentially just your mental load is higher in designing the algorithms. But there's an almost automatic translation. If you tell me how to do it on a suffix tree, you can translate how to do it using just the two arrays. They use much less space. They don't have a dependence on the alphabet in the sense that the suffix tree had. And we've seen two algorithms today to compute both arrays in linear time. And they're a bit more tricky than many of the things we've seen, but not too crazy.